lectures on asymptotes, combined power functions, and where functions meet. Again, we're going to start with a warm-up of our normal distribution stuff as well from before. So we've got question 1. A random variable x is normally distributed with a mean of 20.5. So we should write out mu equals 20.5 up here. So mean equals 20.5. Just a reminder as well that you need your calculator, so make sure you've got that handy. Mean is 25 and standard deviation is 4.3. So we can write sigma equals 4.3. Make sure to write those things out. They tend to say the word normally distributed in the question for you, which helps you to give you an idea that this is what you're doing. Find the probability that x is greater than 22. So that's what that stands for. P stands for the probability, meaning the area, that x is greater than 22. So are they asking for a boundary or for a probability? They're asking for a probability. They gave us a boundary. So it's going to be the case where we go second vase, and if they want a probability, we select 2, normal CDF. If it's the opposite, they gave us a probability and they want us to find the boundary, we would do 3, inverse norm. So it's a good idea to do a little sketch. So the mean's 20.5, so 22 is going to be to the right of the mean. So let's do a little sketch of our normal distribution, because quite often you'll get a mark for method if you do this. So do your little normal distribution. I tend to do the curve first, and then I do the line underneath, marking the mean at 20.5. So 22 is obviously going to be to the right because it's higher than 20.5. And they're saying probability that x is greater than 22. So meaning that area up here. So try to think what would be the upper and lower bounds for this one. And just in case you're asking what I mean by that, select normal to CDF because they want us to find the area. Remember, we have to put in the lower and upper boundary. So clearly you can see the lower boundary is 22. So that's easy enough. So let's mark in lower boundary 22. Enter. Upper boundary is positive infinity. Can you remember what we put in for positive infinity? Have a think. That's right, it's 1e99, so 1 times 10 to the power of 99. So where is the E button again? I'm forgetting myself. Where is EE? Here it is, so just above the comma. So to activate E, you've got to go second comma 99. So that's how we put in positive infinity. That's just a massive number, like 1 times 10 to the power of 99. So that's close enough to positive infinity, we've decided. And we've got to put in the mean, which is 20.5. And the standard deviation, have a look, what is it? It's 4.3. 4.3, go to paste. Let's see what our answer is. Nice. So again, write your answer written out to lots of decimal places first. I didn't have space to do that, but you will have plenty of space. So write it out to lots of decimal places first, and then round it to 3 sig figs. So this rounded to 3 sig figs would be 0.364, because next to the 3 is a 6. So that rounds it up. 0.364, lovely. Same thing again. Find the probability that x is somewhere between 18 and 22. So 18 is to the left of the mean, and 22 would be to the right of the mean. So let's do your normal distribution, sketch, do your curve, do the line, mark in the mean line. 18 would be to the left, 22 would be to the right. Probability that it's in between these two. So there's obviously our lower boundary is 18, our upper boundary is 22, so that's an easy one. It's nice if you get one like that. So let's go back to second vase. A normal CDF because they want a probability. Our lower bound is 18. Our upper bound is 22. And our mean and standard deviation are the same, so that's easy. And enter. Write this out to lots of decimal places first. Make sure to write 0 point, don't write point, because sometimes the examiners can't see that you've written point. Write 0 point. And to 3 sig figs, that would be 0.35, have a think. Yep, that would be a 6, because next to that is next to the 5 is a 9. 0.356. Done. So here's a bit different. They might want you to find a boundary. Find k such that the probability that x is less than k equals 3. So this is the inverse step where they've given you the answer, they've given you the probability, they want you to go back and work out what the boundary is. So let's do a little sketch. So 0.3 is less than half. So remember, like the normal distribution, the mean splits it into 0.5 area and 0.5 area, because probability is the same thing as the area under the graph. 0.5 of the area, 0.5 of the area. So if x is less than k is equal to 3, so if the area to the left of k, less than k, k is the boundary, is equal to 0.3, then it's got to be to the left of the mean, because this whole area represents 0.5. So if it was something like 0.6, it would be up here, because 0.6 is more than 0.5. So 0.3, it's got to be down here. They want to know what our upper boundary is, which is good, because what has to go into the calculator when you do inverse norm, it has to be the area to the left, not to the right. So that's good, but they've given us the area to the left, like probability x is less than k. If they did give us the area to the right, remember we just do 1, which is the whole area, minus that area. And that would tell us what the area to the left was instead. So it's an inverse norm problem. Let's clear, let's go second vase. Select inverse norm this time because they want us to find the boundary. The area to the left is 0.3, put in 0.3. Mean is 20.5. 20.5. Standard deviation is 4.3. Because normal distributions are a pretty new topic, you could probably pretty much say for sure it's going to be on the exam. And they almost always seem to get you to do a normal CDF question, like find a probability, and an inverse norm question. But you never know what's going to happen this year. So what's the... they want to know basically what is this upper boundary. And that makes sense because it should be a boundary that's somewhere to the left. Like the mean is 20.5, 18 point something is to the left. It shouldn't be to the right, bigger than 20.5. So that makes sense. So it's good to critically analyze your answer. Write that out fully, unrounded, and then round your answer to 3 sig figs, which would be 18.2. So k is 18.2. That's what this little upper boundary is. Oh, that took a while. Let's go on. So this is a question that has the doppelganger of Lillian Ritchie. This is not actually Lillian Ritchie, but it just happens to look a lot like Lillian Ritchie. Underwater, pulling a face. All right, in a competition to see who could hold their breath underwater the longest, the times were normally distributed with a mean of 150. So write out mu equals 150. And a standard deviation of 12 seconds. And they're both in the same units, which is important. If one was in minutes and one was in seconds, you'd have to convert the minutes ones to seconds. They have to be the same units. But they're both seconds, so we're good. The top 15% of contestants will go through to the finals. What time is required to advance to the finals? So do a little sketch if you want. Do your normal distribution. The top 15%, what's 15% as a decimal? Divide by 100. It would be 0.15. And the top 15%, so meaning the top ones, this area here has to be 0.15 because that's the top 15%, not the lowest 15%. They want to know what is the time, so what's the minimum time to get into this, what's the lower boundary. But remember, when you do inverse norm to find a boundary, you have to put in the area to the left. So what would be the area to the left? And that's pretty easy. It would be 1 minus this area, because this whole area by definition is equal to 1. So the area to the left must be 1 minus 0.15. So make a little note of what you're doing so the examiners see what you're doing. Area to the left is 1 minus equals 1 minus 0.15. What does that equal? It's 0.85. So that goes into our little calculator. Let's get the calculator going. And we're finding a boundary. We're finding what's this boundary. So second vase, we want inverse norm. We're not asked to find, we're told the probability. Or we worked it out as 0.85. So the area is 0.85. The mean this time, it's 150. That's why it's good to have these things written out. It just helps. Just make sure you write down the right number. That's important. If you write down the wrong number, it's messed up. Paste. Okay, so they got the amount of seconds that it takes to get into the final is you need to be able to hold your breath for 162 seconds rounded to 3 sig figs. So again, write it out unrounded first, so that if you make a mistake in rounding, you'll probably potentially, hopefully not even lose a mark. So 162 seconds. So Lillian's doppelganger, if she wants to get into the finals, she has to hold her breath for at least 162 seconds, which is the lower boundary. So that's a long time to hold your breath. Let's move on to question 3, which is a bit tricky. So the distribution curve corresponds to, so remember this means x, the random variable x, is approximately normally distributed with a mean of mu and a standard deviation of sigma. That's what that means. Now this is a tricky one. Area A equals area B equals 0.2, but I have seen this come up on a past exam, this kind of question, so pay attention to this. Area A equals area B equals 0.2. So they drew this for you. So area A, what did they say it equals? That equals 0.2. Makes sense, it's less than 0.5, so that's easy. What does B equal? The same as A, they said. It's 0.2. Again, makes sense, it's less than 0.5, less than half. So they want us to find the mean and the standard deviation. To do that, we will probably be using the boundaries here. So notice that because that's symmetrical, so use the symmetry of the graph is what I've written here. So it's a symmetrically distributed normal distribution. It always is in this case in our topics. So therefore, if that's 0.2 and that's 0.2, then 20 and 38 must be equal distance from the mean. So the distance between 20 and the mean must be the same distance as 38 and the mean. So you've just got to find out what number is exactly in the middle of 20 and 38. You can do that intuitively if you want, but if you're not sure, I'll make a note of that, sorry. The mean must be exactly in the middle of 20 and 38. So that's what that says. The mean must be exactly in the middle of 20 and 38. You can try to work it out yourself, as I said, intuitively. Or if you want a method, you could just find the average of these two numbers and they'll tell you what's in the middle. So to remember to find the average of these two numbers, you add them together and divide by 2. So you're finding the mean to get the mean. So the average of those two. 20 plus 38, plug that into a calculator over 2, use your alpha y equals to make a nice fraction. And 29 is the mean. There you go, mu. 29 is the mean. So we've found the mean. What I found tricky, this question came from the Math Studies textbook, but the only way I can think to find the standard deviation for this question is using a formula that's from SL Maths instead of Math Studies. So what I did in the end, I said, let's just cancel this question because finding the formula that you use in SL to find the standard deviation is not part of our course. So I just said, okay, sure, let's just say, I'll just tell you what it is. So sigma equals 10.7, and you're not expected to calculate that because, as I said, you calculate it with a formula that's not part of the Math Studies course. That could be just an error of the publishers of the textbook. So we'll move on from there. You just write that down because you need it for the next parts. So calculate the probability that x is less than 35. So they want an area, so it's a normal CDF. So 35, the mean we've got has been 29, so do a sketch. Mean is 29. So 35 must be to the right of the mean because it's higher than the mean. And they want the probability that x is less than, so they want to know this area. So what's our lower boundary? It would be negative infinity, so negative 1e99. Our upper boundary will be 35. So let's go. Second bars. They're finding probability, so we want 2 normal CDF. Lower is negative 1e99, so negative 1,99. Our upper boundary is 35, that's a 35 there if you can't see it, because that's what the question has. 35. What's our mean? Our mean is 29. And our standard deviation has to be the answer I gave you, 10.7. There you go, and write that out unrounded again, and then think what would that be rounded to 3 sig figs? That would be 0.713, because next to the 2 is a 5. So 0.713. Lovely. And next, find the probability that x is between 23 and 30. So do a little sketch, label it, mark in your mean at 29. 23 must be to the left of the mean because it's less than 29, and 30 must be above the mean because it's to the right of the mean because it's higher than 29. Alrighty, so let's plug that in the calculator. That's easy when they just give you the left and right boundary. It's easier than putting in 1e99, so this is a nice question. Second bars, they want a probability, so it's normal CDF, not inverse norm. Lower is 23. Our upper boundary is 30 according to this question. Just make sure to put in the right numbers. Mean and standard deviation are the same as before because it's the same question. So write the unrounded 0. Blah blah, and then what would that be to 3 sig figs? 0.24, but next to the 9 is a 7, so it rounds it up. So it rounds up the 9, which rounds up the 4 to a 5. So we shouldn't write 0.25 because that's 2 sig figs. We should write 0.250. That's now 3 sig figs because this 0 here, it's trailing and after the decimal point. So that's why these three numbers are now significant. So that's the end of the warm-up finally. Let's go on to the beginning of the lesson. So we're on to the lesson about asymptotes, combined power functions, and where functions meet. So you'll be using your GDC to do a lot of graphing today, so make sure to have that handy. So as I said, basically for this section, all you need to do is to make sure your graphing skills are up to scratch on the GDC. So you've did a bit of graphing in the past, like in IB1, and you did maybe a little bit also in, especially when you did sequences and series, finding intersection points. And you might have done a little bit of it when you've done coordinate geometry. So it's basically just graphing and being really accurate and being really good at adjusting the window so you can see intersection points and intercepts and stuff like that. For example, you would be required to enter a given function into y equals, so i.e. typing in that little button there, y equals, I'll just clear what's there. So you'll be required to enter in a function, for example, 2 to the power of x minus 1, that kind of thing. So you'll be required to enter a function into a graph if you're given the function. So, and if you need to make nice fractions, like if you need to make an awkward function like alpha, that has fractions in it, so you could just use a nice fraction button. So for example, I could go alpha y equals, while I'm in here, and select numerator denominator, makes a nice fraction, like 5x over 2 to the power of x. You can even do fractions within fractions if you want, like that kind of thing. See, 2 to the power of x over 4. So using the alpha y equals button is good. That's a real messy looking function. I'm getting rid of it. Yeah, so using this alpha y equals button is very helpful if you need to put in nice fractions. Y equals is where you go to start to put in the graphs. You'll probably be required to adjust a window. Like, so imagine I graph that. Oops, press the wrong button. So I graph that. Quite often you might be required to adjust a window if there's a nice exponential function. Maybe I need to adjust the window to see it a bit higher. So remember window. I might need to adjust, if I need to see a bit higher up on the graph, I need to make my y max bigger. So you might need to adjust your x min, x max, y min, y max quite a bit. So you can adjust your graph, i.e. if I want to see a bit higher for some reason on my graph, I go to y max, and I could make it like 20, for example. And you'll see the graph goes up a bit higher, although that was hard to see. It doesn't finish at 8 now, it finishes at 20, so it goes a bit higher. So possibly adjust that. Another thing you could do is if you're in a bit of a rush, to adjust your window, sometimes first of all, I go zoom, standard first, and then I manually adjust the window, depending on what kind of graph it is. So just showing how you go to zoom standard. Zoom standard is a 616. Zoom standard, notice what it does, it resets it back to negative 10 to 10, negative 10 to 10. But imagine I also had another thing in there, like 3000, and I need to find the intersect of those two functions. So I can't see it because my graph only goes up to y equals 10. So I'd have to make my y max something greater than 3000. So for example, greater than 3000, i.e. playing up today, 4000 graph. So notice now that my graph goes all the way up to 4000 here, so hopefully I'll see the second function. Here's the one that we had before. Here's that second function, y equals 3000. And I unfortunately can't see where they intersect, so I couldn't find their intersect. So I would have to make my x max a bit bigger. make it something like maybe 50. Let's have a little look. Quite often Xmax doesn't need to go beyond 100, but occasionally it has. But your Ymax could be a huge number, depending on what the other function is. Just taking a little while for this one to come through. Yep, so see here's function 1, here's function 2. Imagine they wanted me to find where they intersect. So I go second calc, so second trace opens up calc, intersect 5, which is, and then first curve you just go enter, enter, enter. There it is. There's the coordinates of my intersection point. So the coordinates of my intersection point at 12.6 and 3,000 obviously. Okay, so back to here though. As a little sample of what you're kind of required to do today. So I tend to go, as I said, zoom standard first. It just resets it to -10 to 10, -10 to 10, and then start to manually adjust the window. You might be asked to find the coordinates of any vertices, like any turning points. So remember to do that. To find coordinates of any turning points, you would go second calc, and if it's a maximum, you select maximum. If it's a minimum, you select minimum. You might be asked to graph a second function, like I did. I graphed 2 functions, and find any points of intersection, like I just did before. And remember to do that. I went second calc intersect, number 5. You might be asked to find any x-intercepts on the graph. Turns out the functions I just drew don't have x-intercepts. But if they did have x-intercepts, I would go second calc. And they want you to find, second calc 0. I'm doing this one. Find the x-intercepts. I would go second calc, select 0, and then start to find the x-intercepts. To find any y-intercepts, by y we mean like where does the graph cut the y-axis, for example, then you would go second calc value and enter in the x value given. So if I notice it cuts the y-axis here at x equals 0, so I would go second calc, select value, and enter in the x coordinate of that intersection point. The x coordinate is at x equals 0. If you look down here, 0, enter. There it goes. It told me y equals 5. That's the intersect, sorry, not for this one, but for that one. If I want to find the intersect for the other one, I just need to arrow closer to it. Oh, actually, it just went straight there. That's nice. Y equals 3,000. Otherwise, I would arrow close to it and go second calc 0 again. Work out when any horizontal or vertical asymptotes might be. Remember, they're the dot, dot, dot lines, like exponential function. This exponential function has an asymptote at 0. To do that, you might need to trace. So there's a trace button here. Oops, it's gone off. So trace, and just try to see, this graph's getting closer and closer to a value, but I'm not sure what it is. So the y value, note what's happening to my y value. It's getting closer and closer to 0 as I trace. That's a really small number, and it's e times 10 to the minus 4, but it's never crossing 0, so I've got an asymptote at y equals 0. So all those kind of things, but we'll be doing that a lot in this lesson. Okay. So rather than erase as I go, I've got these written up already, and I'll just talk to you through it as we go. So here's an example. Consider the function, weird functions we're kind of dealing with now. Y equals 1 over x to plus 2, 1 over x plus 2 plus 4. Find the asymptotes of the function, find any axes intercepts like x or y intercepts, sketch the function including the features from a and b. So the first thing you would do is you'll go to y equals and you're going to graph it. So let's do that together. So I'll clear these ones. So y equals, I need to clear what's in there, that's important. Y equals, and notice, let's use our alpha y equals to make this nice fraction. So use alpha y equals n slash d to make the fraction. That's what that says. Alpha y equals n slash d means numerator denominator. So let's put in 1 over x plus 2, 1 over, see x is here, x plus 2, then arrow out of the fraction because the 4 shouldn't be in the fraction, plus 4. And so we just go woohoo, let's graph. Remember, it's good to maybe go zoom standard to begin with. So once that's finished, go zoom standard 6, zoom 6. Always a good spot to start, and then you can adjust it if you need to. So I see that's made the graph a bit clearer for me because I was so zoomed out before. Find any asymptotes of the function. So this one looks like it's got an asymptote, like it looks like it's never going to touch through that line. So it looks like there's going to be a dot, dot, dot going through here. There's also a horizontal asymptote. Have a guess, where do you think that might be? That's right, it's just through here. So if you're to find those values, remember we can trace. So let's click trace. Let's find where the horizontal, oh, if you want, let's find the vertical one first, why not? So go along here to find, oops, to find what x value are we getting closer and closer to, because it's an x, it cuts through the x-axis. Yes, asymptote. Oops, I think it's jumped onto the next one. So notice it gets closer and closer to -2, but never quite touches -2. It jumps to the other side instead. So we've got an asymptote at -2. You can do this, you can answer C now if you want, you can start to sketch it. Just do your x and y axis, label x, y, put a little arrow on them. Do a vague sketch like this. And then our dot, 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 our vertical asymptote should be at x equals -2. Let's see what is the y value that of the asymptote. So trace along. What is our y getting closer and closer to, but never quite touching until it skips to the next graph? Looks like it's getting closer and closer to 4, doesn't it? Never quite cuts. Yep, it gets closer and closer to 4. So let's just say 4. Y equals 4 for our horizontal asymptote. So our two answers for the asymptotes. So as I said, so a little explanation of what we did. Use the trace button. Using the trace button, you can work out if there is a horizontal asymptote at y equals 4. That was our horizontal one, and a vertical asymptote at x equals -2. So they're regions that the graph never touches. These graph lines here, they get closer and closer to those asymptotes, but they never cross them or touch them. So vertical asymptote at x equals -2. B, find the axes intercepts. So let's have a look in our graph to see what kind of intercepts there are. Looks like there's a y-intercept here and an x-intercept here. So I'm going to find the y-intercept first. So y-intercept, let's see. So to find y-intercept, remember, we do a lot of second calc. Y-intercept, at the y-intercept, the x is 0, so we press value. So the y-intercept occurs when x is 0. Enter. There it is. So when x is 0, what's y equal to? Y is equal to 9/2. So or 4.5. So 9/2 is the same as 4.5. So our y-intercept is at 4.5. So y-intercept is at x equals 0. Another way you could do it is you could just sub in x equals 0 into the equation and calculate it. 1/0 plus 2 in the calculator using alpha y equals to make a fraction plus 4 gives you 4.5. Or you can do what we just did. Second calc value and type in 0. So we went second calc, selected value, typed in 0. It told us that the y-intercept is 4.5. To find this x-intercept, which happens to be over here because it cuts the x-axis here, we've got to go second calc zeros. So instead of saying intercepts, they call them zeros on the graphing calculator. We've got a left bound. It wants us to be arrow, so we're slightly left of the x-intercept. So here's the x-intercept. Slightly left of it would be a bit this way. So up there, press enter. Right bound, they want us to arrow, so you're slightly right of the x-intercept. Oops, gone too right, I think. So the x-intercept is here, so we're slightly right of the x-intercept. Press enter. And then guess means press enter one more time. And see it flashes where it should be. Our x-intercept is at -2.25. So to write that out, you would write x-intercept, you go second calc 0. You could click left, click right, you can write that in too if you want. X equals -2.25. So it's quite fiddly, this graphing, as you can see. Here's another one. Again, I filled it all in just because it's maybe easy for you to see the whole thing written out as we go. Use technology, so hint, use your graphing calculator, to help graph y equals 2 to the x over x. Oops, not that one. We want this one. So actually I shouldn't press second, just y equals. Let's go back to there, y equals, clear that. And it's a fraction-y one, so let's go alpha y equals to make a nice fraction. And we'll go 2 to the x, so 2 to the power of x over x. Pretty crazy function. Says your graph should include any axes, turning points, and asymptotes. So let's graph it again. So again, I tend to just go zoom standard to begin with. Zoom standard, zoom 6. And notice it slowly graphed this crazy looking function. So it's a pretty weird one. So to do a basic sketch of it, draw your x and y axis, x, y, label y, put a little arrow on them. It's a pretty crazy function that's kind of curving like that, so I've done that in red. Pretty crazy function curving like that, so I've done that in red as well. It's looking to me like there's an asymptote this way, like it's never going to touch that one, and it's looking like there might be an asymptote going through the x-axis too. So to find those, remember we can trace. So press the trace button. Where's it ended up? Oh, can't see the cursor, so just start arrowing. So trace x, it's looking pretty close to 0. That's moving away from 0 though. Yeah, it's getting closer and closer to 0, but not quite touching. So x is 0 for this, x is 0 for that one. Horizontal asymptote will cut through y. So let's see, what is this y value getting closer and closer to? Keep an eye on the y. It's looking like it's getting closer and closer to 0, or at negative 0 point something, it's getting closer and closer to 0. It's not crossing 0. So we can write y equals 0. So remember, use trace, horizontal asymptote at y equals 0, vertical asymptote at x equals 0. And to draw them in, you do dot, dot, dot lines. They have to be dot, dot, dashed lines when you're doing asymptotes. Let's see, by the look of it, because they're asymptotes, that doesn't seem to cross the x or y axis. So there's no x or y intercepts, which is kind of interesting. So that's kind of fun. We don't have to take it. We don't have to work it out. But there is a turning point. So notice this is not a turning point. It's just the graph kind of goes like that way. But this is a proper turning point because it goes down and then it turns up. So whereas this one still just keeps going down. So turning point, remember to find a turning point. If you're not sure, go second calc. And it was a minimum because it was a bottom turning point. So it's not a maximum. So it's a minimum. So left bound, like we did with the x-intercepts, we've just got an arrow so we're slightly left of the vertex or the turning point. Takes a while, let's just keep moving along. There we go. So see the turning points here, I'm slightly left of it, press enter. Right bound, arrow so you're slightly right of it. This is fiddly work, but you need to get good at it because this stuff's always on the exams. Enter, you're at the right. Guess, yep, we do want you to guess, so press enter. See, it's flashing on the minimum now. So the coordinates of the minimum are 1.44 is the x coordinate, the y coordinate is 1.88, 3 sig figs. So we should write that there's a minimum at brackets 1.44, comma 1.88, because that's how we write our coordinates. And the way we did that, we graphed it obviously and went second calc minimum. So that's all the important features of that graph. Let's go on to the next page. Here we are. And again, I'm just going to leave the answers on there, but I'll talk you through it because it's kind of hard to read the answers anyway. And also, it's just nice to have it written out as we go. So consider the function fx, that should be an equal sign by the way, equals x squared plus 1 over x. Find any vertical asymptotes, find the turning points, find the axes intercepts, the x and y intercepts, and sketch the function. So you might want to go straight to sketching the function, and then we'll just add the other things afterwards. So let's throw that into our GDC. Let's go y equals, let's clear the current function that's there, and x squared, so just go x, you can use the square button if you want, plus 1 over x. So plus, let's go alpha y equals, numerator denominator, 1 over x. Let's arrow out of there. Yep, that looks right, doesn't it? X squared plus 1 over x. Let's graph this. See how crazy it looks. Crazy function. Look at that. So you might want to go zoom standard, but I've already done it. So I can see just by the way it looks. Zoom standard, crazy looking function. So draw your x-axis, label it x. Draw your y-axis, label it y. Don't deal with the asymptote yet, but let's just sketch the graph. So it's kind of going zoom, cuts the x-axis, We don't know what that value is, but we'll find it out, so just leave that off for now. Just draw the red line. There's that function, and here's a little funny curvy thing going on there. So that's the function, and now we're going to slowly work out what all the values are. So it's looking to me, it doesn't look like there's any x asymptotes, because this graph just goes on infinitely in both north, upwards and downwards directions. This section of it does. So no asymptotes. It doesn't seem to be horizontally, but there's definitely, looks like there's a vertical asymptote here. And I'm guessing it's at x equals 0. Remember to work that out. To check that, we can trace. So just, if your cursor doesn't turn up, just start arrowing and you'll see it pops up. Let's see, so x, I'll show you back to where we were. So x, it's looking pretty close to 0. Look at x, it's getting closer and closer to 0. And then, oh, that's interesting. But yeah, and notice that even though it says x is 0 here, there's no y value, so meaning it doesn't exist. There is an asymptote that cuts through there. And the whole reason why there's asymptotes, it's to do with the fact that you've got x in the denominator. Do you remember the idea in maths that we can't divide by 0? Not allowed to divide by 0 in maths. That's an error on your calculator. So if you plug in x is 0, this whole thing becomes an error. Hence why x is 0 is an asymptote. It's a region of the graph that doesn't exist according to the rules of mathematics. So yep, and see, like it's going to the negative decimals and getting further away from 0 now. So we can now mark in our asymptote, our vertical asymptote, ... do your dashed line, and you should label it x equals 0 is our vertical asymptote. So we've done A. Let's do B. Find any axis-intercepts. So there looks like there's a y-intercept here, and I've already labelled it, but we need to know how to find it. It doesn't seem like this one doesn't cut anything. Sorry, that's not a y-intercept, that's an x-intercept. There's no y-intercepts by the look of it. So x-intercept, remember to find an x-intercept, we go second calc zeros, because another name for x-intercept is the zeros. So we've got our graph, let's go second calc zeros, which is the second one. And remember, we've just got to click to the left for the left bound and click right to the right bound. So arrow away, just got to be somewhere left. Yep, that's left. Left bound, yep, we did that. Right bound, yep, we're clearly right of the y-intercept, the x-intercept. Enter. And guess, yes, we want you to guess, so please guess for us. Calculator, there you go. So the 0 is at x equals -1. We already know that it's at y equals 0. So x equals -1 you can label as being the x-intercept there. So second calc 0, we got x equals -1 and pop it on your graph. There is no y-intercept, because see this graph, it doesn't cut the y-axis, it just keeps going infinitely up this way because of this asymptote. It's not allowed to touch it. They want us to also find any turning points. So no turning point here, that's just some weird line, but here is a curve and it goes down and then up, so that's a turning point. So is it a minimum or a maximum? Just think, yes, you're right, it's a minimum. So let's go second calc, select minimum, the third one. Again, we've got an arrow left and right, so we've got to just click to the left, press enter, go to the right, press enter, and let's do that now. So keep arrowing. Oh, so it's a bit confusing. See, I'm kind of not really sure if I'm left or right of it, so just make sure you clearly are left. You know, that's clearly left. See here, it's hard to know, am I right? So just make sure you're clearly right. Yes, please guess, calculator. Yep, our minimum is at, the coordinates of the minimum are 0.794 and 1.89, that would round to. So minimum at 0.794, 1.89, I popped it here, but also I've written it here. Minimum at 0.794, comma 1.89, close brackets. Make sure your coordinates are written in brackets using second calc minimum. It's good to write this down because you don't have to go back and watch the video again to remember how to do this. You can look at your written notes. Here's an example, trying to make it a bit more real-worldy. A theme park water slide is constructed according to the function, a weird function. W with respect to x is equal to negative 0.0125x cubed plus 0.3x squared minus 2.35x plus 12. So this is a cubic function because the highest power of x is a cube. Where w is the height of the slide above the ground. So this is basically a map of the slide. If you graph this, you'll get a map of the slide. W is the height of the slide above ground, and x meters is the horizontal distance from the starting position. How high is the starting position above the ground? So basically, how high is it above the ground? You might want to sketch it first. Let's just sketch it. Sketching is a good way to start. Let's enter in this function. Negative, so use the negative button, 0.0125. Make sure you're typing it in right. X cubed, x to the power of 3. Arrow right to get out of that. Plus 0.3, 0.3 x squared. I'm going to use the square button. Minus 2.35x, I think it's meant to say. Hopefully, yep. Minus 2.35x. And what comes next? Plus 12. Let's have a little graph of that. You know it's still graphing if it's kind of spinning up here. It means it's just thinking about things. So we can't see the graph very well. And it's because of this plus 12. So that's with zoom standard. So I want to make my y max a bit higher because I want to see up here somewhere. And I want to make my x max a bit higher because I want to see out here. We don't need to go lower, so we don't need to adjust the y min or the y max. So y max is going to be higher, maybe something like 15. And x max, who knows how like many meters long could the slide be? So maybe I'll put in 20 and just see what happens. So window, so we're putting in x min's fine, x max 15 because the slide could be 15 meters high. Oops, that was meant to be the y max, sorry. So the y max should be 15 because that y max tells you, talking about how high the slide is. X max is like how wide it is, so let's put in 20 and see if we can see the whole slide, the graph of the slide, or the graph which represents the slide. That looks a bit better, doesn't it? Nice. So technically, the slide's not going below ground or before the starting position. The slide is really just from here to here. Finishes there, starts there. So when I do my little sketch, I'm just going to sketch this region. So I wouldn't bother sketching outside here or down there because it doesn't make sense in the real world. Just sketch these ones because it's a real world situation. As we said, the slide doesn't go underground, we're assuming. Okay, so what they want to know is how high is it above the ground. So they want to know what that little height is there. So you could just find the y-intercept. You could go second calc, value. At the y-intercept, x is always equal to 0. Enter. It's 12. So that's a way you could do it. You could also do what I did here. At x equals 0, this function, and then just plug in 0 wherever you see x, is negative 0.0125, brackets 0 cubed, plus 0.3, brackets 0 squared, minus 2.35, brackets 0, plus 12. You can pop that in the GDC and just work out the answer, and you get 12 as well. So both ways are fine. B. The water slide ends in a pool, which is at ground level. So the water slide ends here, it's at a pool at ground level. How far away is the pool from the starting platform? Here. So they basically want to know what that length is there. To work out that length there, you probably want this little thing, which is the x-intercept. Remember to find the x-intercept, you'd go second calc, zeros. So number 2, we need to arrow so we're just left of it. You know, that's a bit too far left, so just go. So you're only a little bit left of it. There you go. So left bound, we're a bit left of it. Enter, right bound, arrow so that you're slightly right of it. Yep, that's clearly right. Enter. Guess, yes please, guess calculator. It's telling us 16, so the length there is 16. So 16 is what we do. So I said just find the x-intercept using second calc zeros, and then you click left and right bounds. X is 16 meters. Don't forget your units because it's a real life situation. C. Supporting structures hold up the water slide at the turning points. So the turning points may be here and here. So there's little support structures, like, you know, basically there's a beam here and a beam here holding it up. at the turning points, how far from the starting platform are they? So they want to know what's this length here that would support that beam, and what's that length there that would support this beam. So to do that, you could find the coordinates of this turning point, this minimum, and this maximum, and then you could just use the x-coordinate. So it looks not so clear on my one, but see, this sort of turns and goes up a little bit. This turns and goes up. If you're not sure, you could trace. Oops, not tracing properly. Need to go in there. Trace. You can see the y value goes up to 6 point something or 5 point something, and then it drops a bit. See, it's dropping again to 5. So that told us that that was a maximum. And then it drops and then kind of goes up again. So that's a minimum. So to find this minimum, we'll go second, trace, select minimum, choose the third one. Arrow so you're left of the minimum. It's a bit hard to see, so just make sure you're clearly left. Arrow so that you're clearly right of the minimum. It's kind of hard to see where it turns, so just go a fair bit right this time. Don't go too far over. Enter. There it is. So we only need the x-coordinate, by the way. So the minimum is at x equals 6.85, because next to the 4 is a 5. 6.85 is our minimum. So minimum bracket 6.85. You could also put in the y-coordinate if you want, 5.96. So you could go bracket 6.85, comma 5.96, close bracket. So I've written them here. Minimum is at 6.85, 5.96. And so we only need the answer. 6.85 is how far wide that one is. They now want to know how far horizontally must this beam be. So let's find the maximum. So let's start again. Second calc. Maximum is the fourth one. So we're clearly left of that maximum already, so enter. Now let's arrow so that we're right of the maximum. Right of the maximum, enter. Quite fiddly this, isn't it? So round to 3 sig figs, that maximum, its x is 9.15 and its y is 6.04, because next to the 3 is at 8. So that coordinate would be, the maximum would be at 9.15, comma 6.84, close brackets. And you can pop it on here, bracket 9.15, comma 6.84, close bracket. And it says, so there, and it said using second calc maximum, this would be using second calc minimum. So this beam, so there is going to be 6.85 meters from the starting point, and this beam will be 9.15 meters from the starting platform. And now we're on to here. How tall are the columns? So that's basically the y-coordinate. So that's why it's worth recording the y-coordinate, because you never know, you might need to use it in a later question. So saves you having to go through doing all that again. So how high are they? This one would just be the first y-coordinate. It's going to be, where is it again? 5.96, and then the other one was 6.04. That one, 5.96 is how tall that one is. 6.04 is a bit taller, that one. All right, so thank goodness that one's been done.